In the previous two videos, we talked about section 7.1, which was all about confidence intervals. We're going to continue that in section 7.2 and section 7.3. I'm going to combine these into just a single video. So this video might be a little bit long, but I think it's best to just combine these into a single video because they basically just deal with the remaining formulas that we haven't talked about. But the strategy for attacking these problems is pretty similar to section 7.1. So let's look at the three formulas that we haven't discussed so far. These are part of 7.2 and 7.3. So the first one that I want to look at is this one. This is how to determine the confidence interval for estimating a population proportion, or a percentage, given a sample proportion or percentage. So what's meant by this is, let's say you're trying to estimate something like the percentage of right-handed people in a certain population. There is a specific population proportion of right-handed people, and we can try estimating it by using a sample proportion. So we might take a sample of some group of people, figure out the proportion of people that are right-handed in that sample, and this is the formula that we'll use to determine the confidence interval for the actual population proportion P. And I've given you a little key over here on the right side that tells you what all of these letters mean. P is the actual population proportion, so that can be expressed as a fraction or a percentage, something like that. So you might say that 85 or 90% of the population is right-handed. P hat is going to represent the sample proportion, so the proportion that you get just from your specific sample. And there's also a Q hat that appears in this formula. The Q hat is just 1 minus P hat. So for example, if P hat represents the proportion of right-handed people, Q hat would represent the proportion of left-handed people. It's just the rest of the people. Okay, so that's one formula that we'll use in this section. The other one that I want to talk about for a second is this one. This is the confidence interval for estimating a population mean like we did in the previous video, but this one applies whenever you have small samples. So remember, we've talked about how whenever your sample size is at least 30, the distribution for the sample mean that you get is going to be roughly normal. So it will be a normal distribution. Unfortunately, whenever you have smaller sample sizes, so a sample size smaller than 30, you don't get a normal distribution. Instead, what you get is a t distribution. So we'll call it the t distribution for these smaller sample sizes. But notice that this formula is very similar to the one right above it. So the only difference here is that instead of using a z value, which comes from the normal distribution, we'll be using a t value instead. And thankfully, this t value can also be computed using a table, and I'll show you how to do that in just a bit. But the main thing that I want to point out right now is just that these formulas are very similar. So they're basically the same thing. The only difference is that whenever you're working with a small sample size, you have to remember that we're using this t distribution rather than the ordinary z value that we've been using. So this next page summarizes a bunch of differences between the normal distribution, so the standard normal distribution we've been calling z, and then this t distribution that I've been talking about. You can read over this page a little bit more carefully if you'd like in your own time. There's not a whole lot that I expect you to know about the t distribution except for these three things. So I expect you to know that the standard deviation is more than 1, so it's not exactly the same as a standard normal distribution. The t distribution requires something called degrees of freedom, but computing the number of degrees of freedom is relatively easy. The number of degrees of freedom that you'll need to look up your t value is just going to be your sample size minus 1. So this says your degrees of freedom is n minus 1. So just keep that in mind whenever we start using this table. And then the rest of this page is basically just summarizing that t is what we'll use anytime we have a small sample size. So whenever the sample size is smaller than 30, and in other contexts, whenever the sample size is larger than 30, you can just use the normal distribution. Okay, so That covers these two formulas that I wanted to talk about at the beginning, and then there's one other formula that we're going to need today, and that's this necessary sample size to estimate a proportion. So that's similar to the necessary sample size that we needed to estimate a mean, like we have right beneath it, and it's derived in the same sort of way. But this is the formula that we'll be using to decide how many people we need to sample in order to appropriately estimate some population proportion. Okay, so those are all of the formulas that we're going to need in this section. I think it'd be best to just dive right into the examples. So let's look at example 4, I think is when we left off. Yeah. So we'll look at example 4. So in example 4, what we're talking about is how to determine a t-value or a t-score, just like we were determining these z-scores. So here, notice that, like I mentioned before, a t-distribution has a certain number of degrees of freedom. And in this case, we were just told the number of degrees of freedom, it's 13. And we're supposed to estimate t of 0.05. And just like in the previous video, that 0.05 is supposed to represent the area that we have over here to the right. So that would be the area on this this right side over here. So let's look at how to find this t value using a table. So I will pull up this distribution table. Here is the distribution table that I gave you for the z-scores. So you have the z values here and then another page with the positive z values. If you look at the very next page, you'll see a table for the t distribution. Now notice this table is a little bit different. So this table, as its top row, has the different confidence intervals that we might want. We'll use those in a bit. And then the next row tells you the area in a single tail. And then the third row tells you the area if you wanted it in both tails. So notice, for example, maybe let's look at this one. If you want a 90% confidence interval, then that means that the area of 0.10 is in the outside. So that's the area in the two tails on the outside. So this area on the left plus this area on the right would be 0.10. If you wanted the area in just a single tail, it would be 0.05 rather. So that's where all of that comes from. And notice that for any of those measurements, so in this particular problem, let's see, we wanted t of 0.05. So that means that in a single tail, we want an area of 0.05. So I'll come back over here and we'll look at the area for one tail with 0.05. So this is the t-value that we're going to want. But in order to decide the appropriate t-value, we have to also plug in the number of degrees of freedom that we have. So in this problem, we were told that the number of degrees of freedom is 13. So I plug in the number of degrees of freedom, which is 13, and then I find the appropriate area that I want, which is 0.05, and then the intersection of those will tell me the t-value that I'm looking for. So in this part, the t-value will be 1.771. So I'll come back over to this page, and I know that t of 0.05 is equal to 1.771. So that's how we use this table with the t distribution. Notice that in this case, it's a little bit easier to read the table, I think, but you have to remember to plug in the right number of degrees of freedom, and then you also have to interpret this number correctly. I'm still considering this subscript to just be the area that we want to the right side of this, or in other words, in this right tail. Okay, and we'll do the same thing down here. So here there are 18 degrees of freedom, and we want t of 0.1. So that means I want 0.1 to be the area in the right tail. So I will, there we go. I will look at the row that has 18 degrees of freedom, and I want 0.1 to be the area in that right tail. So if I look at the intersection of those, I get a t-value of 1.330. So that's the t-value that I'm going to record on the next page. So that's a 1.330. If you'd like, you can just write it as a 1.33 or a 1.330. Either one is fine, but that would be t of 0.1. So that's how we're going to use this table involving the t-distribution. Let's see how to apply that in practice. So here it says in example 5, a simple random sample of 25 incidents of pickpocketing yields mean losses of $513 with a sample standard deviation of $262. If the loss due to pickpocketing is normally distributed, find the 95% confidence interval for the mean loss mu. Okay, so notice that in this case our sample size is 25. That's not big enough for us to use the ordinary normal distribution. So we'll check off these assumptions. We do have a simple random sample, which is what we need in order to apply any of the formulas that we've talked about. Now, we don't have a large sample, but we do have that the thing that we're estimating is normally distributed. That is, the losses for pickpocketing are normally distributed. And that's what we'll need in these cases. But because the sample size is smaller than 30, we'll be using that t-distribution, which is sort of approximately normal, rather than the ordinary normal distribution. And it's also true that the population standard deviation is unknown. So that's a good hint that we'll be using this t-distribution. So the t-distribution, maybe I should mention, is used whenever the number of incidents, or maybe I should say your sample size, is smaller than 30, or when your standard deviation is unknown. So for both of those reasons, it's a good idea to look at this t-distribution. So first, it says for a confidence level of 1 minus alpha, find t sub alpha over 2, with the number of degrees of freedom equal to n minus 1. And we wanted the 95% confidence interval. So if we want the 95% confidence interval, that means that the area out here on the boundaries is going to be the remaining 5%. Oops. So the area on both tails would be 0.05, and that means that alpha over 2 would be 0.025. So we can use any of this information to find the appropriate t-value, but notice that in order to look up this t-value, we're going to need to plug in the number of degrees of freedom. So you should decide how many degrees of freedom you think there are in this problem. If you want to pause the video and think about it for a second, then you're welcome to. But in this case, the number of degrees of freedom is always just going to be n minus 1. Here, n should be 25 because our sample size was 25. So it'll be 25 minus 1, which is 24. So that's the number of degrees of freedom that we'll use in the table. And in the table, we want a 95% confidence interval, which is the same thing as saying that we want a 5% area from both tails, or a 0.025 area for a single tail. So let's look up that information in the table on, oops, sorry, this navigating this is kind of troublesome. Okay, there we go. So we'll look up the corresponding information over here. We found that the number of degrees of freedom was 24. And we also wanted a 95% confidence interval. So notice that the three pieces of information that we wrote on the last page a second ago are all right here. So you can either just look up the required confidence interval, or the amount of area that you need in one tail, which was 0.025, or the amount of area that you need in both tails, which was 0.05. All three of these are equivalent to each other. So it doesn't matter which one of those you think of as being the thing that you're looking up for this column. Either way, we're in this column, and we're in the row corresponding to 24 degrees of freedom. And if I look at the intersection here, I would get 2.064. So that's the t-value that we're interested in. So we'll have 2.064 as our t-value. So that means that if I come back up here, I will have a t-value, t sub alpha over 2, of 2.064. So that's the t-value that we get in step 1. So notice this is pretty similar to what we did with z-values. It's just that because our sample size is smaller than 30, we need to use this t-distribution and the t-table instead. But the rest of the problem is going to be very similar to what we did previously. If you need to find the confidence interval, the formula is almost exactly the same, except instead of the z value here, we have the t values. But we'll still be using the same approach. I just need to plug in x bar. So x bar in this case is 513, because that's our sample mean. And then I'll have minus our t value, which was 2.064, times the sample standard deviation, which was 262.23, divided by the square root of n, where n is your sample size, so that would be divided by the square root of 25. And that will give us the lower end point for our confidence interval, and the upper end point will be given by this side of the formula. So it will be the same thing, 513.32 plus this time 2.064 times 262.23 divided by the square root of 25. So at this point, I can just plug in all of the information that we know on the left side and right side of the formulas to get our confidence interval. This left side, if you plug it into a calculator, gives you 405, and the right side in a calculator will give you 621, and that gives you the confidence interval that we're looking for. So in other words, the actual population mean will be between 405 and 621 with 95% confidence. Okay, and that's the interpretation that I'm looking for down here. So what I should say is that we can be 95% confident that the population mean loss from pickpocketing is between this $405 and $621. So the procedure is very similar to what we did in the previous video. The main thing is just that because the sample size is smaller than 30, we can't actually use the normal distribution, we have to use this t distribution. But to compute a t value, we're still just using the same thing that we did for the ordinary normal distribution. You're just going to use the table to compute the appropriate t-score. Okay. So let's look at example 6 here. Here it says, a study conducted by Sallie Mae and Gallup respondents found that 323 out of 1,000 students paid for their education by student loans, and we want to find the 90% confidence interval of the true proportion of students who paid for their education by student loans. So here we're looking for a true proportion, and all that we have is a sample proportion. So I've written the formula that we're going to use down here at the bottom, but maybe let's go ahead and write down what these proportions are. So the sample proportion would be the proportion in our sample that paid for their education by student loans. So that would be 323 out of the 1,000. That's the proportion from our study that paid by student loans, and that would end up being a 0.323. So a proportion, just like a percentage, should always be some decimal or fraction between 0 and 1, or if you want to write it as a percentage, it'll be between 0% and 100%. So that would be p hat. Q hat is 1 minus p hat, so that would be the proportion that did not pay by student loans, and that would be 0.677. Our sample size was 1,000. And then there's one other thing that we're going to need in our formula. So notice that down here, if you wanted to start tackling the confidence interval, the only missing thing that we have in this formula is, in order to estimate this population proportion, we need to know this z-score, z sub alpha over 2. And in this case, that alpha over 2 is going to come from this 90% confidence interval. So again, what you can do is you can draw the little picture like I've been doing. So we want 90% as our area on the inside. That means that we want 10% to be the area on the outside, and that would leave a 5% area over here on the left and a 5% area over here on the right. And that means we're looking for the z-score that has a 5% area to the right, or in other words, a 95% area to the left. So you could go through all of that, but I want to remind you that we do have this nice table on the first page of this set of notes. So I'll scroll back up to that. And this table tells you for a given degree of confidence that you're looking for, it'll tell you what the area on the outside is and also what the z-score with half of that area to the right is. So if we wanted a 90% confidence interval, then we're just looking at this z-score 1.645. So we saw that in the previous video, but I just want to remind you we have this little table for the 90%, 95%, 98%, and 99% confidence intervals. So you don't always have to use the big Z table to look those up. You can just use this small table. Okay, so we're looking at a z-score of 1.645. That's what we're going to plug in into this formula down here. So I have the z sub alpha over 2 is 1.645. And now I'm just going to plug in all of this information up here into these formulas down here. So on the left side, I can plug in the sample proportion, the z-score we just found, and the rest of that left side, and that will be the lower boundary for the actual population proportion. And then the upper boundary is given by the same sort of thing. We just plug in all that information on the right side. If you evaluate the left side here, you get a 0.30. And if you evaluate the right side over here, you get a 0.35. And that gives us the confidence interval that we're looking for. So in other words, we're 90% sure that the true proportion of students who paid for their education by student loans is between 0.30 and 0.35. Or if you want to phrase it as a percentage, we're 90% sure that 30 to 35% of students pay for their education by student loans. Okay, so let's look at example 7. In example 7, it says a healthcare professional wishes to estimate the birth weights of infants. How large a sample must she select if she desires to be 98% confident that the true mean is within 0.6 ounces of the sample mean? So notice here, she wants to be sure that her answer is correct within a 0.6 ounce error. So this will be the error in our estimate. And I've recorded the formula here. This is the same formula that appears up on the first few pages, but just so that we don't have to keep scrolling, I thought it'd be good to just re-record the formula here. So remember, this n represents the required sample size, and now we just need to plug in all of the information that we need here. So if I want to be 98% confident, then I need first that z-score that corresponds to a 98% confidence level. And for that, again, you could do the big picture thing, or you can scroll back up to the little table and look at your 98% confidence level. That would give you a corresponding z-score of 2.326. So that's the z-score that I'm going to use here. So the z-score that we need here is 2.326. So I'll scroll back down and use that z-score. We'll have a z-score of 2.326. So that's what goes in place of this z-score. Now, it's also important in the prompt that we knew what the actual population standard deviation was for these birth weights. The standard deviation was known to be 8 ounces. So that 8 would go here in place of the sigma, and the error that we're allowed to tolerate is a 0.6. So that's how I would compute n. If you plug that right side into your calculator, what you'll get is 961.8, and whenever you're working with these sample size estimates, you should always just round this number up, because you can't have a decimal sample size like this. Instead, we're going to take a sample size of 962. So in other words, we would have to study 962 birth weights to average those, and then we would be sure that our answer, or our sample mean, was within 0.6 ounces of the actual mean. We would be 98% confident of that result. Okay. So this is the last new exercise, this exercise 8.1 Exercises 2 and 3 here are just sort of a review of section 7.1. So we'll talk through this one. This one is going to apply the last new formula that we talked about, which is this one. It's the sample size that you would need in order to estimate a proportion. So let's look at this exercise. It says, a manufacturer of golf equipment wants to estimate the proportion of golfers who are left-handed. And they want to know how many golfers they would have to survey if they want to be 99% confident that that sample proportion has a margin of error of 0.025. So in other words, they want their sample proportion to be within 2.5% of the actual proportion. That's what this margin of error is saying. And they want to be 99% sure of that. Okay, so I think for this one, I will scroll back up to the formula that's relevant here, just so that I can point something out. So in this formula, there is a little note that says use a p hat value of 0.5. Notice that if p hat is equal to 0.5, then so is q hat in this example, because remember p hat and q hat add up to 1. So in other words, if you don't know anything about the underlying proportion, you can just use 0.5 as your p hat value and then 0.5 as your q hat value if you don't have any estimate for those things. Okay, so that's what we'll use. And we also know that we wanted to be 99% sure in this case. So I can come up here and look at the 99% degree of confidence. That has a corresponding z-value of 2.576. So that's the z-value that we'll be using in this formula. Okay, so I'll scroll back down to that example. So we saw already that 2.576. That's the z-value that we found just a second ago, so I'm just plugging that into this formula. Now, if there's no estimate of the proportion available, then remember that we're taking p hat and q hat to both be 0.5. So I'm replacing both p hat and q hat with that 0.5. And then I'm dividing by the error e, which was 0.025 in this example. So if I just plug all of that information into the formula, it will give me the sample size that I need. And if I plug that into a calculator and round it up, I get 2655. So that's the number that we would have to survey in order to be that confident with our appropriate margin of error, assuming that we had no estimate of that proportion available. Now notice that if you do have an estimate of the proportion available, then things change a little bit. So if you actually do have an estimate of the proportion, so in this case 15% are estimated to be left-handed, then p hat would be 0.15. That means that q hat would be 0.85, because it's the rest of the 1. And then these other terms are exactly the same. But notice that in this case, the number of people that we have to survey is a little bit less. It would be 1354. So if you do have some estimate, then that will benefit you in terms of the number of people that you have to go out and survey to get an accurate assessment. But if you don't have any estimate, we can still come up with some number of people that we need to survey, but we need to take p hat and q hat to both be 0.5. So that's sort of the worst case scenario in these problems. Okay, so that concludes section 7.2 and section 7.3. The other problems are review problems. I'll talk through them quickly in a second, but if you'd like, you can just ignore the rest of this video or try working those problems on your own first and then look through the rest of this video. But I'll talk through these. They're just a review of section 7.1. So in problem 2, it says a random sample of 45 salaries of NCAA football coaches has this mean and this standard deviation, and we want to construct a 95% confidence interval for that mean salary. So we're just using the mean confidence interval that we had up above. Now in this case, because our sample size was 45, we can use the z-score rather than the t-score that we talked about at the beginning of this video. It would technically be a good idea still to use the t-score, so I'll let you use either of them, but I think just to make our rules a little bit easier to apply, I'm just going to say that you can use the z-score anytime your sample size is bigger than or equal to 30, and you can use the t-score anytime your sample size is smaller than 30, just to make a nice clean rule. Okay, so what we need to do is plug in all of this information on the left side and this information on the right side to get our estimate. We know X bar from the prompt. We also know the sample standard deviation from the prompt. And then we know N is 45, and I can look up this z-score from that table at the beginning of this set of notes. Something that I do want to mention about computing these, it tends to be pretty easy to plug in this left side and this right side into your calculator. If you have a calculator that remembers what you typed in, you can just plug in the full left side and then go back and backspace to this minus sign and change it to a plus sign. So that'll save you some time in plugging these in. The only difference between these two expressions is the sign in the middle. So if you have a calculator that has the ability to just backspace over that particular sign, then you can just change it from a minus to a plus sign, and that will give you a quick way of computing these two endpoints. But those are the endpoints of the confidence interval that we're looking for. Okay. So the next example is similar. It's actually exactly the same, just with some different numbers. So I'm not going to go over this one in too much detail. You can look through it. But the idea is still the same. Because the sample size is larger than 30, it's okay to just use a z-score here. However, there is something interesting to be said at the very end here. It says, what would happen to a confidence interval like the 1 and 3 if your sample size is increased? So what happens to a confidence interval if we increase the sample size? Well, what happens whenever you increase the sample size is the margin of error that you have for your study will shrink. And that means that that confidence interval would also appropriately shrink. So you can imagine something like this. If I was only allowed to survey 3 or 4 people, then I would have a huge margin of error. I wouldn't expect my results to be very close to the actual population mean. But if I'm allowed to sample almost the full population, then my margin of error is very small. And therefore, my confidence interval can be pretty small. I can be pretty sure that my actual population mean lives within a small interval. So that would be a more precise measurement. Conversely, if the level of confidence was increased, so if we needed, instead of being 90% sure, if we needed to be 99% sure that the actual result was in our interval, we would have to stretch out our interval a little bit more to allow for a little more variance in our measurements. So in order to be more certain of an estimate, we'll have to expand the interval. In other words, maybe just to give an example, I could have a pretty small range that I'm 50% confident will cover the actual population mean. But if I needed to be 99% confident that the population mean was in that range, I would have to stretch out that range a little bit more. So if we want a higher level of confidence, then the confidence interval will grow. Okay, and that's all for this set of notes. That's actually all that we're going to talk about this week. So that's it for this week. This is also the last topic that will be included on our next exam. So our next exam is just going to focus on Chapter 6, which is what we talked about before the break, and then Chapter 7, which is what this set of videos was about. So this is everything that we need. Your exam will be sometime next week, but I'll be emailing you with more information about that. So again, feel free to email me if you have any questions, and I would be happy to help if I can.